The Chambon Dam was built in the 1930s in the Romanche Valley, below the ski resorts of the Oisan Range. The dam, which is 90 metres high and 294 metres long, is subject to the phenomenon of alkali aggregate reaction, which was first noticed in the 1970s. As a result, the concrete is swelling at a rate of 50 microstrain per year. The first consolidation work was carried out from 1992 to 1997, with a view to ensuring the safety of the structure and guaranteeing its long-term operation. Major investigations were then conducted from 2007 to 2010, and a digital model was built. These gave a clear idea of the consequences of swelling in the concrete and helped prepare for further work in 2013 to 2014. With a view to controlling the effects of concrete swelling, a new series of 7 slots, ranging in height from 16 to 42 metres and totalling 2,500 square metres, was cut using 16mm diameter diamond wire. The work was carried out by 2 concomitant teams and completed in 6 months. 415 horizontal pre-stressed tie rods cross the structure from upstream to downstream. The cables are made of greased and sheathed T15 strands. The centre lines on both the upstream and downstream sides were positioned beforehand by surveyors working in cradles suspended from cranes. The entire 4,200 metres of drilling was done from scaffolding on the upstream side, with no more than 1% deviation being permitted. Special tools were developed to handle and place the tie rods. Each tie rod holds a maximum of 15 square metres of upstream face and is placed according to a standard grid. The following types of tie rod were used: 1T15 in the lower part, 7T15 in the upper part, and 9T15 in places. The tie rod anchors are held in recesses in the upstream and downstream faces. The upstream anchors are passive and were ultimately embedded in the second stage concrete. The downstream anchors are active and adjustable so that they can be adapted to later swelling of the concrete. In addition, the tension in 66 representative tie rods in various parts of the dam is monitored remotely via vibrating wire strain gauges. Residual tension in the tie rods must always be between 2 limits. A lower limit, corresponding to the earthquake-induced pull-out force, which absorbs the seismic energy as stress and not strain. It's equal to the amplification caused by the structure multiplied by the horizontal ground acceleration of 0.18 g multiplied by the mass of the block. An upper limit equal to 80% of the strength of the tie rod, allowing for concrete swelling over a period of 20 years and differential expansion of the steel and concrete. The consolidation work was designed to last for 50 years, taking into account continued swelling of the concrete at the rate of 50 microstrain per year. The threaded section of the downstream anchors therefore had to be between 6mm and 36mm long. The tie rods and anchors are doubly protected against corrosion. The tie rods have a PVC sheath, greased strands, and an outer HDPE sheath injected with grout. The anchors are protected by a wax-filled cover. Also, on the downstream side, the recesses are covered. On the upstream side, further protection is provided by second and third stage concrete, an HDPE cover, and a sealing membrane. Lastly, the system is completed by a carbon mesh on the upstream side. This consists of 1,400 strips of carbon fibre bonded with epoxy resin to create a composite material. The strips, which are 20 to 30 centimetres in width, connect the heads of 2 adjacent tie rods vertically, horizontally and diagonally. In all, 6,000 metres of strips were installed, averaging 4 layers thick. The carbon fibre strips are connected to the upstream tie rod anchor blocks, which are made of reinforced concrete. Thus, if stress is exerted on a strip, the pull-out force is transmitted directly to the adjacent tie rods. As they're designed to hold the entire upstream facing, the tie rods do not have to be oversized. Deformation of the carbon strips is assumed to have a catenary shape. Full-scale qualification tests were performed using a test slab specially built on site. It was thus possible to define the input data used in the dimensional design. To ensure the watertightness of the dam, a new stretched and drained carpi membrane was placed on the upstream face, covering a total area of 9,000 square meters.